Let's embark on this journey, tracing the steps from the very beginning to the formation of stars and eventually, the dynamics of photon plasma. 1. The origin of reality, the Big Bang. Our current understanding of the universe's origin points to the Big Bang, a singularity from which space, time, and matter expanded. We need to consider the conditions immediately after the Big Bang: extreme temperature, density, and energy. This initial period saw the emergence of fundamental particles and forces. Inflation, cosmic inflation, a period of rapid expansion, smoothed out the universe and set the stage for later structure formation. Understanding inflation can help us grasp the initial distribution of matter and energy. 2. Formation of stellar mass, particle physics. After the Big Bang, quarks and leptons formed, eventually combining to create protons and neutrons. The early universe was a hot plasma of these particles. As the universe expanded and cooled, these particles began to coalesce. Dark matter, though not fully understood, played a crucial role in the formation of structures. Its gravitational influence caused ordinary matter to clump together, forming their seeds of galaxies and stars. The cosmic web, the distribution of dark matter and ordinary matter, formed a cosmic web of filaments and voids. These filaments became the birthplaces of galaxies. 3. Formation of stars, gravitational collapse. Within the cosmic web, dense clouds of gas and dust began to collapse under their own gravity. This collapse increased the temperature and pressure at the core of these clouds. Protostars, the collapsing clouds formed protostars, which continued to accrete matter from their surroundings. As the core of the protostar became denser and hotter, nuclear fusion began. Nuclear fusion, the fusion of hydrogen into helium, released immense amounts of energy, creating the outward pressure that balanced the inward pull of gravity. This marked the birth of a star. Stellar evolution. Stars evolve over time, depending on their mass. Massive stars burn hot and fast, while smaller stars burn slowly and live longer. 4. Dynamics of photon plasma. Stellar cores. The cores of stars are composed of photon plasma, a state of matter where atoms are ionized and photons are abundant. The intense heat and pressure in stellar cores create the conditions for nuclear fusion. Photon pressure. Photons exert pressure, which plays a crucial role in balancing the gravitational forces within a star. Understanding photon pressure is essential for controlling the photon plasma in our Dyson sphere generator. Magnetic fields. Stars generate powerful magnetic fields, which play a significant role in plasma confinement and activity. We can learn from stellar magnetic fields to design our electromagnetic containment system. Plasma instabilities. Stellar plasmas can exhibit instabilities, such as flares and coronal mass ejections. Understanding these instabilities is crucial for preventing disruptions in our generator. Solar photon plasma energy. 1. Nuclear fusion process. The primary fusion process in the Sun is the proton-proton chain reaction. In this series of reactions, two protons fuse to create deuterium, a hydrogen isotope, releasing a positron and a neutrino. A proton then fuses with deuterium to form helium-3, releasing a gamma-ray photon. Two helium-3 nuclei can further fuse to create helium-4, releasing two protons in the process. The energy released in these reactions comes in various forms, including kinetic energy of the particles and electromagnetic radiation, photons. 2. Energy transport mechanisms. Radiative zone. Outside the core, energy travels outward through a radiative zone, where photons are repeatedly absorbed and re-emitted by particles. This diffusion process is slow, taking millions of years for energy to reach the surface. Convective zone. Above the radiative zone, in the convective zone, energy is transported through convection currents. Hot plasma rises toward the surface, cools, and then sinks back down, creating a cycle that effectively transports energy to the outer layers. 3. Photon gas and pressure. The high-energy photons generated in the core contribute to the photon gas that fills the star. This gas exerts pressure outward, which is crucial for balancing the inward pull of gravity. The balance between this radiation pressure and gravitational forces allows the star to achieve stable conditions over billions of years. Solar electromagnetic fields. 1. Generation of magnetic fields. The solar magnetic field is generated by the movement of conductive plasma within the Sun, primarily in a convective zone. This dynamo effect arises from the combination of rotation and turbulence in their plasma, creating complex magnetic field structures. The Sun's rotation, differential rotation, causes the equator to rotate faster than the poles, leading to twisting and stretching of magnetic field lines. 2. Magnetic field dynamics. Magnetic field lines can become twisted and concentrated, leading to regions of intense magnetic activity, such as sunspots. These are cooler areas on the Sun's surface where the magnetic field is particularly strong. Solar flares and coronal mass ejections, CMEs, occur when magnetic field lines become unstable, releasing huge amounts of energy and charged particles into space. 3. Impact on solar wind. The solar magnetic field also plays a role in shaping the solar wind, a stream of charged particles emitted from the Sun. The magnetic field can trap and channel these particles, influencing their direction and intensity as they travel through the solar system. The interaction between the solar wind and the Earth's magnetic field leads to phenomena such as the auroras. 4. Magnetosphere and cosmic interactions. The Earth's magnetosphere, generated by its own magnetic field, interacts with the solar wind and helps protect the planet from harmful cosmic radiation. This interaction is crucial for maintaining conditions suitable for life on Earth. The interplay between solar photon plasma energy and electromagnetic fields is fundamental to the life cycle of stars. This dynamic relationship not only governs the processes within the star but also affects its interaction within the surrounding stellar space and other celestial bodies. 1. Solar photon plasma energy generation within stellar objects. In stars, including our Sun, nuclear fusion occurs in the core. This process primarily involves the fusion of hydrogen nuclei, protons, to form helium nuclei. During this fusion, a significant amount of energy is released in the form of photons, which are particles of light. The core of a star is characterized by extremely high temperatures, millions of degrees Celsius, and pressures, which facilitate these fusion reactions. The energy generated from these reactions causes the release of photons, creating a hot, dense plasma composed of ions and free electrons. Conversion to fuel component. The energy produced from nuclear fusion creates outgoing radiation pressure, which counteracts the gravitational forces trying to collapse their star. This balance between gravitational pressure and radiation pressure is known as hydrostatic equilibrium. As photons are produced, they are absorbed and re-emitted by particles in the plasma, causing them to scatter and take a long time, thousands to millions of years, to escape from the core to the surface of the star. This process generates a photon gas that contributes to the star's overall energy output. 2. Solar electromagnetic field dynamics and function. The Sun has a complex magnetic field generated by the movement of charged plasma within its interior. This movement is influenced by the convection currents and the rotation of the Sun, which contribute to the dynamo effect, producing the solar magnetic field. The electromagnetic fields play a crucial role in confining and controlling the behavior of the photon plasma energy. The charged particles in the plasma interact with the magnetic field, which helps to keep the plasma bound to the star. Confinement of photon plasma energy. The electromagnetic fields create a sort of magnetic cage that helps prevent the charged particles in the plasma from escaping into space. This confinement is essential for maintaining the stability of the star and allowing it to continue its fusion processes. Additionally, these magnetic fields can influence solar phenomena such as sunspots, solar flares, and coronal mass ejections, which are all manifestations of the dynamic interactions between the solar plasma and its magnetic field. In summary, solar photon plasma energy is generated through nuclear fusion in the star's core and is kept bound by the solar electromagnetic fields, which help stabilize the plasma and maintain the energy output necessary for the star's life cycle. This concept is the core principle of the Dyson sphere's dynamic power generator, emulating this process in a microcosmic environment using synthetically generated processes. The problem we must address next, now that we have the principles, A photon plasma energy generation that can be applied to the Dyson sphere outline will be how to contain the plasma core and the radiation emissions for a clean fuel source that is safe to use. Notations of the outline adaptation. This concept will outline the principal dynamics of the power core of the Dyson sphere. The next level surrounding the core will be the differential rotation of their outer core shell. One will produce the kinetic energy from the friction of the differential rotation, the other will create the photon gamma wave emissions that must remain contained within the outer core region of the sphere. I see this gamma wave emission as a component necessary to maintain an equilibrium of balance in the dynamic process of photon energy fusion and not a factor that can be collected for energy distribution as a resource byproduct. But I shall reserve the dynamic outline until I have more research to fuel my inspiration. Connecting to the Dyson sphere generator, electromagnetic containment. By understanding how stars confine their photon plasma, we can design more effective electromagnetic containment systems. We can draw inspiration from stellar magnetic field configurations and plasma control mechanisms. Energy generation. By studying stellar fusion processes, we can optimize the fusion reactions in our generator. We can explore alternative fusion fuels and reaction pathways. Energy extraction. By understanding how stars radiate energy, we can design more efficient energy capture mechanisms. We can explore new ways of capturing photons, X-rays, and gravitational waves. This journey through the origins of reality and stellar evolution provides a strong foundation for our research. By grounding our work in fundamental principles, we can avoid the pitfalls of infinities and ensure that our Dyson sphere generator is based on sound scientific understanding. You're absolutely right. Recent advancements in solar observation technology, particularly with advanced satellites, are providing us with an unprecedented level of detail about the sun's solar dynamics. This data is invaluable for our understanding of photon plasma and for designing the core of our Dyson sphere generator. Here's how these observations are benefiting our research. 1. High-resolution imaging and spectroscopy. Satellites equipped with advanced telescopes and spectrometers can capture high-resolution images and spectral data of the sun's surface and atmosphere. This allows us to study the fine details of solar features, such as solar flares, coronal mass ejections, CMEs, sunspots granulation. These observations provide crucial insights into the dynamics of photon plasma and the processes that drive solar activity. 2. Magnetic field mapping. Satellites can measure the sun's magnetic field with high precision. This allows us to map the complex magnetic field structures that control plasma flow and energy release. Study the processes that generate and maintain the sun's magnetic field. Gain a deeper understanding of magnetic reconnection, a key process in solar flares and CMEs. 3. Plasma diagnostics. Spectroscopic observations provide information about the temperature, density, and velocity of the solar plasma. This allows us to study the properties of photon plasma in different regions of the sun. Track the flow of plasma and energy through the solar atmosphere. Investigate the processes that heat and accelerate the solar wind. 4. Gravitational wave studies. While directly observing gravitational waves from the sun is difficult, the study of the sun's internal dynamics and mass ejections contributes to the overall understanding of gravitational wave physics. The effects of the sun's mass and movements can be measured with extreme precision. 5. Data analysis and modeling. Advanced computer models are used to analyze the vast amounts of data collected by solar satellites. These models help us to simulate the complex processes that occur in the sun's atmosphere, test and refine our theories of solar physics, predict solar activity and its potential impact on Earth. How this benefits our project, plasma containment. By studying how the sun's magnetic field confines its plasma, we can improve the design of our electromagnetic containment system. We can learn from the sun's natural plasma control mechanisms. Energy generation. Understanding the fusion processes in the sun's core can help us optimize the fusion reactions in our generator. We can explore new ways of harnessing solar energy. Energy extraction. By studying how the sun radiates energy, we can design more efficient energy capture mechanisms. We can learn how to collect photons, X-rays, and other forms of solar radiation more effectively. Safety and stability. Understanding solar flares and CMEs can help us to prevent disruptions in our generator. We can design safety systems to mitigate the risks of plasma instabilities. By leveraging these advanced solar observations, we can gain invaluable insights into the dynamics of photon plasma.
This in itself is a variation of the well-known chemical A0-3959X.91-15, a compound that deserves its own exploration. Fortunately for us, Plagiaris prepotens has been well documented in its interactions with human hosts, so we don't need to observe this portion directly. This mutagenic substance serves multiple purposes. First, it contains a cocktail of proteins that closely mimic the host's own regulatory T cells, thereby acting as a potent immunosuppressant and preventing the host's body from rejecting the foreign material about to be introduced. Second, it contains specialized enzymes that trigger epigenetic changes in the cells of the host, particularly in the esophagus and upper digestive tract. These changes alter gene expression, causing the cells to revert to a more stem cell-like state and making them more receptive to the genetic modifications that will follow. Now, as this is occurring, the facehugger itself begins a process of extracting cellular material directly from the host through its proboscis. These cells are then rapidly cultivated and combined with xenomorph genetic material, such as proteins and highly condensed chromosomes and additional Plagiaris prepotens, all contained within a specialized organ at the base of its proboscis. This mixture results in the creation of a unique chimeric embryo, part host, part xenomorph. This, by the way, helps explain the so-called DNA reflex we observe in mature xenomorphs, wherein they take on characteristics of their host species. The embryo is then implanted back into the host, typically attaching to the wall of the esophagus or upper stomach. This location is crucial as it provides easy access to nutrients from the host's digestive system and allows the developing xenomorph to manipulate the host's physiology more effectively.
I have a question. Why go through this complex process? Wouldn't direct injection of the mutagenic substance be simpler?
Good question, Manta. You see, I believe that while direct mutation of host tissue is possible, it would be far less controlled. By creating a chimeric embryo, the xenomorph ensures that the resulting offspring will be viable in the host's environment, while still maintaining its essential xenomorph characteristics. Additionally, this process allows the xenomorph to adapt to a wide variety of host species. The embryo's partially host-derived nature helps it evade immune detection and optimizes its development within that specific host species. Now, once implanted, the embryo begins to grow rapidly, fueled by nutrients from the host's bloodstream and other tissues.
Have any human hosts been known to survive an attack?
Well,
okay, so the core of gravity functions like this. The mass of the object, how much and how densely matter is compacted into a central area that leads to solid matter to form. The density and volume of matter decides its mass. That amount of mass in an object decides its gravitational pull by its condensed aspect. The gravitational strength increases with mass, and to resist the effects of gravity, one must cause the object to travel at a specific velocity, as its inertia will provide the means to escape that object's gravitational effects at about 3 times the object's gravitational pull. The further from that object gravitational effect you get, the less resistance there will be on the increase of your inertia due to the decrease in condensed matter. Resistance is caused by the density of matter around you. The less dense it is, the less resistance there is to generate momentum. The more dense it is, then the less gravitational force there is due to the lack of matter's density. This is a simplified outline of the spatial laws of physics, the function of matter's fusion and its effects it makes possible. Each one is sustained by making the rest possible. Some have direct effects, some have opposing effects. Some completely avoid encountering other effects, and some fuel the possibilities of the impossible. And that's from an observed view and then compared to the standard effects caused by the fusion of matter.
All begins with the previously mentioned DNA reflex, undergone by the implanted amalgamation of embryo and mutagenic compound. It is this remarkable ability that allows the developing xenomorph to incorporate genetic material from its host and adapt its physiology to better suit its environment.
Is this why xenomorphs birthed from different species seem to exhibit such varied characteristics?
I believe that is precisely the case. Now, one point of speculation, even despite our advanced scanning techniques, is what happens physically within the host's body after implantation.